The first image, captured by the most powerful digital eye in astronomy, reveals something extraordinary. The Vera C. Rubin Observatory in Chile has produced a photograph containing 3.2 trillion pixels, showing a deep cross-section of the universe that captures matter in motion across millions of light years. At first glance, the image appears simple, but closer examination reveals its true nature as a layered tapestry of cosmic structures spanning immense distances and timescales. Sharp, spiked lights scattered across the foreground represent stars from our own Milky Way galaxy, relatively close neighbors in cosmic terms. Behind them lies the remarkable core of this image, a staggering collection of nearly 10 million galaxies displaying every morphological type astronomers have catalogued. Elegant spiral galaxies spin with orderly grace. Ghostly elliptical galaxies glow with the light of ancient stars, and chaotic mergers caught mid-collision show the violent transformation that galaxies undergo when they encounter one another. Each faint smudge and reddish glow represents an entire island universe containing billions of individual stars, planetary systems, and cosmic phenomena yet to be explored. The scale of this single image proves difficult to comprehend. It spans an area nearly 70 times larger than the full moon, as seen from Earth. The field of view is so immense that the Hubble Space Telescope would require centuries to mosaic the same region with similar depth and detail. The Vera C. Rubin Observatory captured this panorama in just 7 nights during April and May of 2025, stitching together 1,185 individual exposures from the largest digital camera ever constructed for astronomical research. The camera itself stands roughly the size of a small car and weighs 3,000 kilograms. It boasts a resolution of 3,200 megapixels, a specification that challenges conventional display technology. To show a single image at full resolution would require hundreds of 4K ultra-high-definition television screens arranged in a massive grid. This technological achievement represents the culmination of decades of planning, engineering, and international collaboration. The first image reveals the southern portion of the Virgo cluster, located approximately 55 million light-years from Earth. This cluster represents the closest large gathering of galaxies to our own Milky Way, and the Rubin Observatory brings it to life with extraordinary detail and clarity. The image displays a beautiful spectrum of cosmic colors created by combining photographs taken through 4 different filters, capturing ultraviolet, green, red, and near-infrared wavelengths. When these separate exposures are combined, they form a color image that conveys crucial information about the objects being observed. The blue shades visible in spiral galaxies come from young, hot stars that shine brightly and indicate regions where new stars are actively forming. The redder colors in elliptical and distant galaxies come from older, cooler stars, the stellar remnants of galaxies that ceased forming new stars long ago. In one picture, both the youth and old age of the universe become visible, showing the full life cycle of galactic evolution. Zooming into a particular region reveals Messier 49, a massive elliptical galaxy glowing with soft yellow light composed of old stars. Because these stars are ancient and cooler, the galaxy displays a gentle reddish tint, a clear sign that it stopped forming new stars billions of years ago. Just to the left sits NGC 4535, a stunning spiral galaxy seen perfectly face-on, shining with bright blue and white light, indicating ongoing star formation. Its spiral arms are filled with gas and dust, and within them are clusters of hot, young stars illuminating the galaxy's structure. Between these two massive galaxies exists a whole variety of others, including a striking two-armed spiral, giant ellipticals, and tiny dwarf galaxies. In the background, like red gemstones scattered across the cosmic canvas, faint reddish smudges mark galaxies far beyond the cluster, some more than 1 billion light years distant. Moving past Messier 49 and its nearby galaxies reveals one of the most impressive spiral galaxies in the entire Virgo cluster, Messier 61. This galaxy provides a rare, face-on view of what the Milky Way might look like if observers could step outside it and see it from above. Discovered almost 250 years ago, it has been a favorite among astronomers. Even the Hubble Space Telescope has studied it in detail. At its center sits a supermassive black hole about 5 million times the mass of our Sun. What makes Messier 61 stand out is its incredible energy output. It qualifies as a starburst galaxy, forming new stars at a much faster rate than typical galaxies. This activity shows in its bright blue spiral arms glowing with the light of young, hot stars. Messier 61 represents a galaxy caught in the middle of its most active, vibrant years, a cosmic moment of peak stellar productivity. One of the most exciting sights in the entire image shows a triple galaxy merger, a rare and chaotic scene displaying three galaxies caught in the middle of a massive cosmic collision. Their shapes are stretched and twisted as their gravity pulls on each other. As they interact, stars and gas are pulled into long tails, bridges, and arcs, creating a dramatic scene frozen in time. Hints of the galaxy's original spiral shapes remain visible, but they are clearly being reshaped by powerful gravitational forces. Comparing the same patch of sky as captured by three different surveys demonstrates the advancement. The Sloan Digital Sky Survey, Pan-STARRS, and finally the Rubin Observatory First Look Image show progressively sharper, deeper, and richer detail, with Rubin clearly revealing features that were barely visible in earlier surveys. Galaxy mergers transform everything about the participants. They can spark intense bursts of new star formation, feed supermassive black holes with fresh material, and eventually create entirely new kinds of galaxies with different structures and properties. Just below this collision appears a much calmer scene showing two perfect face-on spiral galaxies. They appear as a pair orbiting each other, but this is an illusion of projection. The spiral galaxy on the right is about 20 million light-years farther away than the one on the left. They exist nowhere near each other, just two graceful spirals spinning peacefully in separate regions of space. Below the merging galaxies appears a subtle but remarkable sight, a small cluster of faint, reddish smudges representing distant galaxies far beyond the Virgo cluster, all held together by gravity. Their warm orange-red color provides a clear clue that they exist at extreme distances from Earth, their light redshifted by the expansion of the universe. The image reveals more than distant galaxies. Bright objects with long spikes scattered across the frame are not galaxies but stars in our own Milky Way, sitting millions of times closer than the faint background galaxies. The dramatic spikes are not part of the stars themselves, but are caused by the way starlight interacts with the telescope's support structure, creating diffraction patterns. The jagged, sawtooth edges around the image mark areas that Rubin has not fully covered yet, revealing the ongoing nature of the survey. Most objects in this image remain unlabeled, not because they lack importance, but because they have never been studied before. Many have never been seen until now. Thanks to Rubin's unmatched depth and wide field of view, countless new galaxies and structures are finally coming into focus, waiting for astronomers to explore them for the first time. Galaxies and stars are not the only things hiding in this image. Colored streaks cutting across the frame mark the paths of asteroids moving through our solar system during Rubin's long exposures. They are just passing through, but Rubin's software detects them and removes them from the final stacked image, keeping the deep view of the universe clean. In just 10 hours of observing, Rubin detected nearly 2,100 new asteroids flying through our solar system. All other telescopes on Earth and in space combined find about 20,000 asteroids in an entire year. Rubin found 1/10 of that in a single night. Astronomers have identified about 1 million asteroids in our solar system to date, but Rubin is poised to multiply that number fivefold. Within just a few years, it is expected to push the count to 5 million, revolutionizing understanding of the small bodies that orbit our sun. Another stunning image shows a bright, busy region of star formation featuring two famous nebulae, the Lagoon Nebula and the Trifid Nebula. Right in the center, a glowing pink, kidney bean-shaped cloud marks the Lagoon Nebula, a huge stellar nursery about 4,000 light-years away in the constellation Sagittarius. It is so bright that observers can spot it with binoculars or a small telescope. Above it sits the Trifid Nebula, around 5,000 light-years away, full of striking contrasts. The Trifid is especially eye-catching because it combines multiple features in one place: a pink emission nebula, a blue reflection nebula, and dark dust lanes that split it into three clear sections, which is how it received its name. Inside the Trifid, new stars are forming. Their powerful winds and radiation carve shapes into the surrounding gas, providing a vivid look at how massive stars shape their environment even as they are still forming. Together, the Trifid and Lagoon nebulae offer a remarkable view into the earliest stages of star formation, showing how giant clouds collapse, how star clusters come together, and how newborn stars begin to transform the very clouds that created them. A common question arises about what the Rubin Observatory can accomplish from the ground that even a $10 billion space telescope cannot. The answer comes down to how Rubin is designed to work. For centuries, astronomy has relied on still images, snapshots that freeze the universe in a single moment. These pictures have taught researchers much, but they leave out something important. The universe is always moving. Stars explode, asteroids drift, black holes flare, and galaxies collide. Some changes happen in seconds, others over days or years. To understand these events requires more than photos. It requires a video. The Vera C. Rubin Observatory is built to create exactly that, a movie of the entire sky. By scanning the whole visible sky every few nights, Rubin gives astronomers a chance to watch cosmic events unfold in real time, and even rewind to see how they started. It functions like putting a recording device in space that never stops capturing data. Every night, Rubin takes fresh images of the sky. Over time, astronomers stack older images of each region to make a template showing what that part of the sky normally looks like. When a new image comes in, Rubin compares it to the template pixel by pixel. Anything that has not changed disappears from the difference image. What remains are only the objects that moved, brightened, dimmed, or appeared out of nowhere. This method is called difference imaging and proves incredibly powerful. With it, Rubin will spot around 10 million changing objects every single night. Supernovae, asteroids, variable stars, black hole flares, nothing escapes detection. This constant monitoring comes with a flood of data. Rubin will generate about 20 terabytes of raw data every night. Over its 10-year mission, it will take more than 5 million exposures, adding up to around 60 petabytes of data. Hubble collects about 8 terabytes of raw data per year, while the more advanced James Webb Space Telescope gathers around 200 terabytes annually. Rubin will produce a staggering 20 terabytes every single night. In just one night, Rubin will collect more than twice as much data as Hubble does in an entire year. This staggering scale represents not just a leap, but a data revolution that will reshape how astronomy is conducted in the 21st century and beyond.